Linear approximation is one of the applications of differentiation that we're going to look at. It's not a new application, it's something we've looked at before, but it's just phrased a little bit differently and used a little bit differently. So if we look at a function like f of x equal to x cubed, now looking at this function, let us say I want to look at what happens very, very close to the number 2. So I'm only interested in this function for values that are close to 2, for that little portion of the graph. Now this graph is a lovely curve with concavity. It's not a straight line. What we're going to do is we're going to zoom in on this graph close to 2. So we're going to consider that tangent line to that function for values of x close to 2. Now for values of x close to 2, that tangent line is very, very close to the red line itself. The blue line is the tangent line, the red line is the graph itself. But as you can see, the more I zoom in, the more I look at values closer and closer to 2. That graph behaves exactly the same as its tangent line. For all practical purposes, we can use the tangent line for calculations rather than the graph itself. And that's what linear approximation is about. So what we're looking at is we're looking at a function, we're looking at a specific x value because we can't generalize it, but for a specific x value, we find that straight line that we can use to approximate values of that function. Now that is the same as finding the equation of the tangent line. So finding the equation of the tangent line, if this point 2,8, my function is x cubed, I know my derivative of my function is 3x squared, and my derivative in the point 2 is 3 times 2 squared, which is the gradient of the tangent line, which is just 3 times 4, which is 12. And to find the equation of that tangent line, y minus the y coordinate is the gradient times x minus the x coordinate. We're going to rephrase this, but this is the equation of a tangent line. So y is just the gradient times x minus the x coordinate plus that y coordinate. So we're going to use this straight line, Lx, equal to 12x minus 24 plus 8 minus 16. We're going to use this straight line to approximate values for the function x cubed for values of x close to 2. Now we can't use this straight line for anywhere else necessarily, but we can for values of x close to 2. So what does this mean? This means that if I, for example, want to approximate this function in the form in the point 2.1. So if I want to know what is f in 2.1, I know that's going to be approximately equal to the linear approximation in 2.1, which is much easier to calculate. That's 12 times 2.1 minus 16, which gives you 9.2. 24.2 minus 16. So that's what we're going to use for linear approximation. So that is what it means, approximating a curve with a straight line. Now this function concept is expanded when we look at Taylor series and Taylor functions, when we start using polynomials rather than linear functions, but this is just the start of it, linear approximations. So let's take a look. Generally, if I've got a function y equal to gx and I've got a point, that linear approximation is then going to be g, my y value, g of a, plus the gradient, which is the derivative of g in the point a, times x minus the x coordinate. That gives me my equation of my straight line. So this is the same as calculating the tangent of a straight line. We're going to use that for linear approximation. So let's see what we can use it for. A more general question. Use linear approximation to estimate the root of 9.1. So what are we looking at? We're looking at the function square root of x. At values of x, we're looking at x equal to 9. So we want to estimate the values of x close to 9. So we're going to look at that linear approximation. So that's g in the point 9 plus g's derivative in the point 9 times x minus 9. So let's say g in the point 9, the square root of 9, that's 3. The derivative is 1 over 2 root x. So the derivative in the point 9 is 1 over 2 root 9, so it's 1 over 6. So that linear approximation is again going to be 3 plus 1 over 6 times x minus 9. So that's my linear approximation. We can leave it like that, or you can simplify it, but it's easier to leave it like that. So let me show you why. I want to approximate the root of 9.1. So the square root of 9.1 is then approximately equal to the linear approximation at the point 9.1, the straight line's value at 9.1. So that's 3 plus 1 over 6 times 9.1 minus 9. That's why I didn't want to multiply it out, because that becomes simple. 3 plus 1 over 6 times 0.1. So that gives me 3 and 1 over 60, or you can write it as a decimal, 3.0166666. But that is an approximate value of the root of 9.1 using a linear approximation. So let's look at another one. If I want 3.01 to the power 4, if that's what I want to approximate, I'm going to use the function x to the power 4. And my linear approximation is then going to be f in the point. So we're going to look at the point x equal to 3. So f in the point 3 plus f's derivative in the point 3 for the gradient times x minus 3. So let's look at it. F in the point 3 is just 3 to the power 4, which is 81. F's derivative in the point x is 4x cubed. So f's derivative in the point 3 is 4 times 27, which is 108. So my linear approximation is 81 plus 108 times x minus 3, which means f in the point 3.01 is going to be approximately the same as the linear approximation at the 3.01. So this is 3.01 to the power 4 is approximately equal to 81 plus 108 times 3.01 minus 3. So that's 81 plus 108 times 0.01, which gives me 81 plus 1.08, so that's 82.08. And you can use a calculator to see what the exact value, well, you won't find an exact value, you'll find a decimal value for 3.01 to the power 4. 3.01 to the power 4 is approximately equal to 82.0854 and a whole lot more decimals. So you can see this is quite a good approximation. But it only works for values close, not far away. And that is how we use linear approximation to estimate values.